Okay. Welcome everybody to this afternoon plenary lecture. I'm Patrizio Conlaneri. I'm going to chair this session. And really it gives me a great pleasure to introduce the speaker of this afternoon lecture. Professor Anders Rantzer is a well-known researcher and scientist in the area of modeling, analysis, and synthesis of control systems, with particular emphasis and attention to optimization and distributed control. He received his PhD in 1991 in KTH Stockholm under the supervision of Professor Anders Lindqvist. And after some postdoctoral positions in KTH and the University of Minnesota, he joined Lund University in 1993, and in the same university was appointed professor of automatic control in 1999. In his, let's say, long career, he received quite a large number of awards and recognitions, and so for short, I will just mention a few of them. He received the Siam Student Paper Competition Award, the Ifac Congress Young Author Prize, and the IET Award for the Best Article in IEEE Proceedings in 2006. He also a fellow of IEEE, a member of the Royal Swedish Academy of Engineering Science. So since a few years, the scientific interest of Anders has shifted towards the study of positive and monotone systems that are ubiquitous in many applications in networks, especially in biology and in social sciences. Today's talk is indeed on scalable complexity in control problems for positive and monotone systems. So we cannot wait longer for your talk, Anders. So please join me in welcoming Anders to the podium to deliver his talk.
Thank you very much for this nice introduction. Thank you all for being here. It's an honor for me to have this opportunity. So today I would like to speak about how to make control theory more scalable. So I'd like to start by showing you a picture that I took myself when I was in China this spring. And what you see here is actually a water channel without water, because the river is flowing here and there is not enough water to get anything through the channel. So this is a very old example of a feedback control system, because when the water goes above a certain level, it gets diverted into a different direction. And actually, it's more than 2,000 years old. This is a map of the area that I was taking a picture on at the same site. So the previous picture was taken from this hill, and these are the water channels that divert the water from going into the valley and causing flooding of the city of Chengdu and the neighboring area, and instead gets diverted to take a flow along the mountains and prevent a major disaster, which had happened regularly before that. So this is a very old example of a control system, and but actually irrigation systems are still today a very important application area of where control can make a big difference for a large-scale system. So actually, water, even if you come from Sweden, you may not think that water is a big trouble. We have a lot of that. But in many parts of the world, this is a scarce resource, and it's needed for many different things, and many different of uses have different quality requirements, of course, of the water. So altogether, the water network becomes a complex network with many producers and many consumers, and it's clearly a problem where control can make a big difference. So another such area is power systems. So this is a map of the European transmission grid. And the power system area is currently going through a major change due to the introduction of lots of renewable power. So this means that we have more producers, millions of them. Everybody who has a solar cell on the roof can become a producer. But all of these solar cells and wind turbines, they have very variable production capacity depending on weather conditions. And a problem with the power grid is also that the storage is limited. And also, there are many new components introduced on the grid to save power locally, but that at the same time make the control of the entire grid more difficult, because effectively it becomes like negative resistances and help to destabilize rather than stabilize the grid. So there are many other examples. I could mention traffic networks where control challenges include improving throughput, improving safety, reducing the environmental footprint. Or I could speak about communication networks, where again control solutions are important to provide service, accessibility, and efficiency of networks. So all of these examples are large-scale engineering problems where control can play a major role in solving, in making this work, or even making it feasible to maintain a network that is stable and manageable. So what happens then when you go to your textbook and look for methods that can be applied? Then you're facing major difficulties, because one of the first things you see is that you should solve Riccati equations to find optimal controllers. And those Riccati equations has a solution time that grows cubically at least with the number of states. And even once you have computed a solution, you at least need a quadratic number of entries of your solutions to store in your memory. So clearly, this doesn't scale to very large systems. And if you try to use model predicted control, you can easily face even larger complexities, both in the modeling side, but also in the computational side. So how can we deal with systems that have tens or hundreds of thousands of states and interact on a large scale, and still give some kind of guarantees that if all components satisfy model assumptions, the system will work well? This is the way we are used to work in control engineering, not just simulate, but actually use mathematics to analyze what's happening. We need analysis tools and synthesis tools that scale. And the only type of methods that I've seen that scale in this way is those that are based on monotone systems or positive systems. So this is what I would like to tell you about today. And it turns out, luckily, that all of those applications I mentioned so far actually fit quite well into this category in many situations. So this is the outline. I'd like to speak first a bit about linear systems. That's when this term positive system occurs. And I would like to use some very simple models of transportation networks and formation control problems, just to illustrate the concept. So you can ask what's the difference between positive and monotone. Quite often, you use the word monotone system when you are in a nonlinear setting. And the positive is reserved for the linear case. And I will give some examples of nonlinear systems which are still monotone and which are can still benefit from these nice properties. And then I will go to frequency domain and see how you can get a counterpart to a positive system in the frequency domain. Previously we have been dealing so far with state space models. And here I will introduce the notion of positively dominated system, which has many of the features that we have been exploited for scalability before. And finally I'll look at some open problems and some conclusions. So, what is then a positive system? For a linear state space model, we say that this is a positive system if a positive initial state and a positive input will give a positive output. Another way to put it is that the matrices A, B, and C must have non-negative coefficients except possibly for the diagonal of A. If you have a stable system, typically the diagonal of A needs to be negative. And these systems have been studied for a long time. For example, if you deal with probabilistic models where the states are probabilities, you do expect them to be non-negative generally. And economic systems, chemical reactions, ecological systems, in all these areas, these positive systems have been around for quite a while. So there is a big literature in this area, and there are many contributions also in our field of control, which I have not included in this list. This is just some examples of to illustrate some of the literature. And the first thing I would like to illustrate is that this goes at least 100 years back. Perron-Frobenius theorem is a well-known fundamental result in this area. Leontiev was very early to use same type of ideas in economics. There is a classic book on non-negative matrices by Berman and Plemons, but there are also textbooks in our field, like Ciliac used monotonicity ideas in his book from the 70s. More recently, there has been a growing number of applications, and I think papers, and I would think that this is related to the fact that we are speaking about today, that more and more concern in our research field is dealing with large-scale systems, and their monotonicity becomes even more important. So I will give you some examples here of controlled synthesis using linear programming, which goes back to this paper from 2007. And I was also very much inspired by the work by Tanaka and Langbot, who showed how this can be used for distributed controlled synthesis. So here is my first example of a mathematical model for a positive system. So I have a state space model with 4 states, and they represent the content in 4 different buffers. So in every node of this network, there is a buffer containing some commodity. And the content of the buffer is given by the state variable x. And here you see that I have drawn some edges. It means that you can have a flow from this buffer to that one. And this is also indicated, the flow from buffer 2 to number 1, it's indicated by a coefficient L12. And you see that this coefficient appears twice with a positive sign here and with a negative sign there. And it means that whatever goes out from one buffer goes into another one. So that's the reason why those plus and minus signs always come together. And you can also see here that these numbers have a sign pattern, so that if an increasing content in this buffer leads to a larger flow over to 1, it means that this parameter should be positive. And that means that all the off-diagonal elements will become positive, so this will become a positive system. So typically the buffer content will remain positive if the input is positive, and the same is true for the initial state. And here you can ask design questions. So how should I choose these parameters to minimize some performance measure of the system, for example, the gain from disturbance to state? A typical performance measure that we are used to in control. So all the examples essentially I had before would contain questions of the type that can be dealt with this model. But here is another example, which is sort of a dual to the previous one, namely to control positions of vehicles in a formation. So again, I can use the same set of equation, but now the arrow means something else. So the arrow here means that in each node I have a vehicle, and they try to keep their position relative to each other. So here the state variables are position variables. And some of the vehicles can measure their own position. So the first one doesn't really need these L parameters to stabilize, because it can only, it knows its own position, so it can stabilize subject to disturbances. But it's possible also to measure the distance between the first and third vehicle, and these distance measurements can be used to update the state. So here you see that the second vehicle can measure the distance to the first and the third, and use both of those distance measurements to update its position. The fourth vehicle doesn't need to rely on distance measured to neighbors. It can stabilize on its own. So the first and the fourth vehicle have this term, which sort of indicates that they know they can measure their own position, and they don't need to rely on distance to others. Whereas the second and third, they need to use distance measurements. And here you can ask the same question: how do I select these gains to minimize some performance measure, some gain from disturbance to deviations, disturbance to error, in the usual way. And if you compare this model to the previous one, you'll find that the A matrix here is the transpose of what I had before. So previously, I had the same coefficients appearing twice in every column, once with a plus sign and once with a minus sign. Now you see that the same parameter appears twice in every row, again with a plus and minus sign. But again, the natural choice of these parameters is a non-negative parameter value, which means that if the neighboring vehicle comes closer, you move away. Okay, so these are two examples that gives rise to state representations where A is a Metzler matrix, that is a matrix with non-negative elements out of the diagonal. So the positive systems are special when you want to analyze them. Of course, you can do like you do with any linear system, look for a Lyapunov function given by a symmetric matrix. And then you need a symmetric matrix P that solves the Lyapunov inequality. And this symmetric matrix P can then be used to define a Lyapunov function that proves stability of the system. But for a positive system, it's sufficient to look for diagonal solutions to the Lyapunov equation. It means that the search for a Lyapunov function becomes much simpler, and it becomes the number of parameters now scales linearly rather than quadratically with the number of states. But you also have two other options. The third conditions means that you should find a vector. You can think of psi as an initial state which makes all the derivatives negative. So if there is an initial state which makes all the derivatives negative, then the system must be exponentially stable. And that's also if and only if. And finally, you can apply the same criterion to the transpose, of course, and find a vector z that satisfies this inequality. In here, the inequality is vector-wise, so every element to the left must be smaller than 0. So these three conditions correspond to three types of Lyapunov functions. So if you solve the Lyapunov inequality, you will get ellipsoidal level sets of a Lyapunov function, just like you usually do for linear systems. But the ellipsoids are now aligned with the axis because P is diagonal. So if you instead solve for psi in this inequality, that corresponds to a Lyapunov function which has rectangular level curves. And finally, this inequality corresponds to linear Lyapunov level curves of the Lyapunov function. So for positive systems, you can work with linear Lyapunov functions. Okay, so that was, of course, a nice property, but it's even nicer than that because you can now make a distributed stability test. So here is a matrix which is banded, and so I have some zeros here, which makes it possible to illustrate the dynamics in a cyclic graph. So when you update the first state, you see here that the x dot does not use the third state because there is a 0 here. And this is illustrated in the diagram by the fact that there is no edge between the first and the third node. So the first is only connected to the second and the fourth. So this means that in order to check the stability condition, we can divide the test and let one node in the graph be responsible for one row in the matrix. So that's the reason for this color coding. The red first row of the A matrix has an inequality which is checked in the first node. And in order to check that this inequality holds, you only need to know those coefficients of the A matrix that appear on the first row. So the full model is not needed anywhere. You can split up the stability check in such a way that every node only needs to know the coefficients that specify how it's interacting with its neighbors. And this is true for every node of the network. Of course, this stability certificate psi has to be found some way. And in order to find a solution to the inequalities, you have to agree on these numbers because they are used by more than one node. But the very simple way of finding the psi's here is to simply simulate the system. If it's stable, then after a while, all the states will be aligned in the direction of the eigenvector corresponding to the slowest eigenvalue. And it turns out that this is exactly the eigenvector we need to solve the inequality. So you can simulate in a distributed way using Euler's method or something like that. Otherwise, it's a linear program, so you can use distributed methods for linear programming solving. That's what you need for synthesis, because now it's the next step. We don't want to only verify stability, we actually want to find the values of these unknown parameters that makes this matrix stable. So this makes the problem a little bit more complicated. Again, you need to find the stability certificate, which, remember, this is this vector of psi's that we should multiply with to make negative values at every row. But at the same time, we have to find the L. And the L's are multiplying the psi's, so this becomes a nonlinear optimization problem unless you make a change of variables. So now we notice that L1 only appears in the first column, so it only multiplies the psi1 that we wanted to put over here. So we can give a name, call it mu1, the product of L1 and psi1. And the same for L2, and we multiply it with psi2 and introduce a new variable. And then we get a linear programming problem to solve. So now it's nicely convex, and we have efficient algorithms. Actually, by exploiting the sparsity of the matrix, like before. We can run a distributed optimization algorithm and get very nice scalability also for the synthesis part. And once you have found a solution, you can divide the mu with xi to get the desired gains. So notice that this was the structure of the transportation problems. The parameters that I was specifying the flow from one buffer to the other, they appeared pairwise in columns. So if I would have the vehicle formation problem instead, I would have the parameters appear pairwise in rows. So I would have to transpose the system before solving the problem. Okay, so now we can go back to the problem I specified earlier. Let's look at this model and ask, how do we select the parameters to not only get stability, but also optimal performance? So to do that, we have to use another nice theorem for positive system specifying conditions on the input-output map. So this is the transfer function given in the usual form. And we now want to find the parameters of the A matrix so that we minimize the gain of this transfer function. So then there is this theorem saying that the gain is smaller than gamma if and only if this extended matrix is a stable matrix. It has should have all the eigenvalues in the left-out plane. And now you see we are back to a stability problem. So since we know how to solve a stabilization problem with linear programming, we can use the same to also optimize input-output performance. So we can go to our transportation networks, for example, and it's interesting to compare the optimal solutions in 3 different cases. So remember, I have the first buffer and the fourth buffer. They are stable even when there is no transfer between the buffers. So if I put all L's to 0, the first and fourth buffer will be stable, but the second and third will have a problem. They will, if there is a disturbance acting on one of those, the effects will never go away. So the second and third buffer are really relying on transferring material, and so we need to introduce some non-zero values of the L's. So here I have illustrated the optimal solution for 3 different cases. You see here that in all of the cases I have the same disturbance acting on all the buffers, but in the first case I'm most worried about buffer 1 and 2. So it's the error in those 2 buffers that I'm mostly concerned about. And then and the opposite case is over here, where it's the buffer 3 and 4 that I'm mostly concerned about. So here the dotted lines means transfer connections that are not being used. So the optimal solution is only using those connections which has a full error, not the dotted one. So you can compare these 2, for example. You see here that the difference is that in the first one, I'm very much concerned about the first state. So actually, if I have a disturbance on that one, I will transfer that material to the node number 3, even though the node number 3 cannot take care of that itself. It has to transfer it to node number 4, which has these stabilizing coefficients -4. In the second case, I'm not so much concerned about the first node. So this now becomes a transfer which is not being used. So you see that the choice of which connections to use and not to use, which is essentially a combinatorial problem, is now solved by linear programming to get the optimal input-output gain. And in a similar way, you can look at the vehicle formation problem. Then there is a different interpretation. Now remember that an edge means that there is a distance measurement. So the first and the fourth vehicle, they can measure their own position, so they don't need to rely on neighbors. But the second and third, they do need to rely on neighbors. And here the difference in the B matrix means that the disturbance is affecting some vehicles more than others. So if you compare the first and second vehicle, the first one was able to measure its own position, so it's always trying to help the second by using this arrow. That's the distance measurement that the second vehicle is taking by looking at the first. But the other arrows are differing depending on where the disturbance is entering most. So a vehicle which can measure and control its position very well may be reliable, but only if it's not subject to very large disturbances. So if when the first vehicle, depending on where the disturbances hit, you get arrows that are being dotted or full. That's the message. Okay, so this was some of the theory that's available for linear positive systems. And I hope by now that you see that there is a lot to be gained from this positive structure, and you should never ignore it if there is a chance to use it in a large scale system. But the nice thing is that much of these properties are actually propagated also when you go into nonlinear systems. So what is then a nonlinear monotone system? Again, we will look at the state realization. So x dot is a function of the state and the input. And we say that this is a monotone system if the linearization is a positive system for every linearization trajectory. So another way to put it is that here we have illustrated trajectories in the state space, and if you compare two initial conditions where y at time 0 is bigger than x at time 0 in both coordinates, you see this point is above, but it's also to the right when you start. Then as time goes by, this ordering of the two states must be maintained. That's the definition of monotonicity. And it's surprising how often you can actually find this out in applications. We'll see examples of that later. But these, also in the nonlinear setting, this gives rise to very nice scalability properties, because if you have a nonlinear system which is globally asymptotically stable, you can, of course, apply the inverse Lyapunov theorem to prove existence of a Lyapunov function. But here, this is the linear, this is the inverse Lyapunov theorem that proves the existence not only of a Lyapunov function, V, but a Lyapunov function which is separable. And separable means, in this case, that you can construct V by introducing n different scalar functions and just taking the maximum of them. And of course, searching for scalar functions that satisfy the rules of a Lyapunov function is much easier than searching in the high-dimensional space. So also for nonlinear systems, you get scalability from monotonicity. And this illustrates the proof. So I can't resist explaining what this picture is saying. So you start at this upper right corner, and you follow a trajectory, and since the system is globally asymptotically stable, you have to end up in the origin. And now monotonicity says that everything that's in this yellow box at time 0 must be in this rectangle at time 1. So, and at time 2, when the first trajectory is here, everything that started in the yellow box must be in this rectangle. And then as this trajectory goes in towards the origin, the rectangle follows. And everything, every state starting in the yellow box must also go into the origin. So now you can use these lines as level curves to construct a Lyapunov function. That's the idea. Okay, so what are then interesting applications? One is in electrical power networks, voltage stability. I don't expect most of you to have been concerned with voltage stability in power networks before, but it's quite easy to explain what this is all about. I assume that you know Ohm's law. So if you have a set of generators and a set of loads, you can introduce this notation for voltage. And it's all real valued now. No complex numbers to make it more complicated. It's all real valued. So in every node, every generator node, and every load node, you have a voltage. And then you have a network with a matrix of impedances. And this is typically a sparse matrix, sparsity corresponding to the topology of the network. And then once the voltages are given, you can compute the currents that are flowing between the nodes and in and out of the network. So the problem with voltage stability can be explained by looking at this equation. So if you have a load which wants a certain amount of power, then the right-hand side should be 0, because the product of the voltage and current should be equal to the power. But if the voltage goes down, what is this load trying to do? Yeah, it's trying to compensate by taking out more current instead. So, and this is what this equation is saying. If the voltage goes down, so this term becomes bigger, then you increase the current. And of course, this makes things hard and tends to make a power network unstable. And you need some control actions to stabilize the network, potentially. But the nice thing about this is that actually it's a monotone system. And this is not only related to this scalar equation, but also to the fact that all the network impedances are non-negative. So you have to take the signs of this matrix into account to analyze it. But it's a monotone system, so it makes very much sense to use that when you try to stabilize the network in order to be able to derive Lyapunov functions and get scalable conditions. There is actually another thing to be said about nonlinear monotone control systems, namely that if in addition the right-hand side is a convex function, then you have even better situation. Of course, this is always true for linear systems, but for nonlinear, you have to check convexity separately. For a convex monotone system, each component of the trajectory is a convex function of the initial state and the input trajectory. So optimizing these trajectories can be done in general by convex optimization, which is very unusual and wouldn't happen for general nonlinear systems. Okay, here's another application. If you don't want to do power systems, you can do medicine. This equation is describing the evolution of the HIV virus in your body when you have become infected. So here, every state corresponds to a certain version of the virus, because even if you get infected by only one type of the virus, it will mutate in your body. So if you take a medication that kills that virus, there will be a mutation which escapes the medication. So that's the difficulty in treating the HIV virus in the body. So here is an equation which is used by people in that field to describe the mutations. So there is this A matrix which describes what happens if you don't take any drugs. Then the off-diagonal elements of A describes the probability of mutation. Generally, all those off-diagonal elements are non-negative, so it's a positive system. But you can take antibodies, And those will kill certain types of the virus. And these D matrices, which are all non-negative, they tell how effective these different inputs, the drugs, are on different types of the virus. So now the question is, how should I mix different types of drugs to get the fastest possible decay in this system? And this becomes a nonlinear system because you have the multiplication of U and X. So for fixed inputs, it's a linear system, but the design problem is complicated by the multiplication. And actually, it's better to change variables and look at the logarithm of X. And it turns out that in this way, you can get, for an academic example, you can get plots like this. So constant values of the input are the dotted lines. They give a certain decay rate of the virus population. But time-varying inputs, it's almost like switching inputs, can get a faster decay of the virus population. So by changing the combination of different drugs with time, you can more effectively treat the virus population. So experiments are currently ongoing. This was something that was pointed out to me when I visited Caltech, because people were working there with this type of models, and we have since collaborated on how to optimize the composition of the drugs, and that they are testing in the lab. So these plots are experiments on mice. They are not done by the Caltech group, and they are for constant composition of the drugs. And you see here that for certain combinations you can get these virus populations to decay, not only in theory but also in experiments. And hopefully we will see faster decay in the time-varying solution, but that has not been verified experimentally yet. Okay, so I promised you to say also something about frequency domain models. In many situations, you have systems that are partly monotone. But if you model things more accurately, you violate the constraints. That's very common. So the question is now, how robust are these properties when you take unmodel dynamics into account, for example? And this is something that has led us into looking at frequency domain models, because we know, of course, that uncertainty can often be described efficiently in frequency domain. So we want to see what can be done there. So this is one example that ties to what I did earlier, namely the vehicle formation problem. So notice that previously I had just first-order models of every vehicle. And this means essentially that I was ignoring the inertia of the vehicle and assumed that I could change the velocity instantaneously. This is not realistic, at least not all the time. But in some situations, you had better use second-order models of the vehicles. And here you can see I'm again assuming that the first and fourth vehicle can do control on their own, but the second and third are still relying on distance measurements. And here I have introduced two types of parameters. It's the lambda parameters that tells me how I should combine two distance measurements into an estimate of my own position. And the C parameter, which is the controller that is using this distance estimate to make an update of the position of that vehicle. So if you put the problem like this, there is an interesting way of making it into a positive system. And this can be illustrated like this. The C and the lambdas appear like this in the feedback loop. Here the plant is diagonal because every vehicle is independent. The C is also a diagonal matrix because I had a separate controller for each of the vehicles. So only coupling comes through these distance measurements. So the only thing that is not diagonal is this lambda matrix. And what I do now is to first design C so that this closed loop transfer function is what I call positively dominated, which means that the value at the zero frequency should be bigger than the value at all other frequencies. And that can be done separately for each of the vehicles. So this is a scalar inequality. And once I have done that, I can optimize the choice of those weights using scalable methods. But not, because now the only thing that matters is the behavior at zero frequency, and I can use lambda to optimize the input-output gain at zero frequency, and all the other frequencies will, because of this condition, behave well. The gain will be smaller, will not be bigger at any other frequency. Of course, if you have a very resonant system, this is not something you would like to do. It would take a lot of control action to force down this. It could even be impossible to push the amplitude down below the static value. But there are many situations where this is a very simple and straightforward method to bring the system into a setting where you can use scalable techniques. Okay, so I'm starting to approach the end. So I'd like to say something about open problems. There are many open problems in this area. I would say we have just started to do control theory in a scalable way. And of course, we now need to interact with all these kinds of applications to learn what are the right issues, do we address the right questions. But there are some interesting things that we can do already. So for some of the problems that we can solve using these techniques, the H infinity performance that we obtain using scalable methods is exactly the same H infinity performance that we get when we solve Riccati equations. So Riccati equations typically gives us controllers which are not sparse. You have to send all information, all measurements to all places for control. So they are definitely not scalable. But we have encountered many problems where they don't do better anyway. And to understand when this is the case, I think this is a very interesting problem, and we are just starting to understand how that works. Okay, so then of course, many of the applications have saturations involved. So I started out by this Chinese water channel, and of course, before you get above a certain level, nothing happens, but then this channel kicks in and diverts the water. So what you get is a piecewise linear system, and it looks a little bit scary to begin with, because we know that piecewise linear systems, they can do all sorts of nasty things, but it's still a monotone system, so you can still hope to deal with it in a scalable manner. So I think after linear, maybe piecewise linear is a natural next one, but you can go all the way to convex-monotone systems. Remember, that was the class where I had a right-hand side which was monotone and which was also convex when I introduced the input. There we should find a way to design controller that don't destroy the monotonicity, but instead allow us to work with a separable Lyapunov function to analyze the closed loop performance. So altogether, I would say that I'd like to make a comparison to Terry Rockefeller once said that the big watershed in optimization is not between linear and nonlinear, but between convex and non-convex. So I'm starting to believe that the big watershed in control theory is not between linear and nonlinear systems, but between monotone and non-monotone systems. And so that's a quite exciting discovery. So to conclude, we have seen that verification and synthesis for positive systems scale extremely well. Distributed controllers can be computed by linear programming, and even by distributed linear programming, where none of the processors need to have a full model. They can exchange information with each other and iteratively update to find the solution. And if the system is not positive to begin with, it's sometimes possible to use local controllers to give these positive dominant properties that we are looking for. So maybe I should connect back to the beginning. This is actually, if you go to Chengdu, don't miss this opportunity to look at the irrigation channel. Here they also have a statue of this control guy that did this, or actually that was in charge of the whole project. Probably he didn't do any details, but but he's still visible in this form inside this building. That was also visited by Chairman Mao at some point. Okay, so let me thank you for attending and open up for whatever questions there might be. Thank you.
Thank you, Anders, for your inspiring, very well done talk. So, questions are not encouraged normally in these plenary talks, but since you ended so early, I mean, so
I was instructed to leave room for questions.
Sure.
So
now,
I hope so.
We have plenty of time for questions. So if you have any question,
hand over the microphone.
My question is, are there genuine identification methods for positive systems? And in particular also for order estimation for positive systems?
Are there
genuine identification methods for positive systems? And in particular also for order estimation of positive systems?
I mentioned some applications, but I'm not sure what you...
Identification methods. Data-driven modeling for positive
So
systems.
system identification. Okay, thank you. We have been working a bit with model reduction methods for positive systems, so I know a little bit about that. In general, it's hard to enforce positivity when you do model reduction, and this is probably the case also when you do system identification. But there are methods already. Carl Ostrom in the 80s was studying system identification for compartment models, which is a class of positive systems which is common in medicine. So he wrote a thick report about that at the moment, which also has additional references. So certainly people have been addressing the problem of building models. Also, Caroline Beck in her plenary earlier this week was discussing compartment models for medical applications. So it's certainly an area which has been looked into before.
So my question is about optimal control with constraints. So is there any exploitation possible of positive systems when you want to solve constrained optimal control problems?
Yes, I mentioned the convex-monotone setting, and as long as you put convex constraints on the input, it will combine well with those convexity properties that are already present. But you have to watch out when you make compositions of functions, because it's just, if you make a composition of two convex, it doesn't necessarily have to be convex. So it's easy to make mistakes that destroys convexity, but it's doable.
Okay. Any other question? If not, let's thank the speaker. Sorry. No, sorry. There is a question. Sorry.
I'm sorry, just a short question. You've mentioned you've done model order reduction for positive systems. May I ask what kind of methods have you used?
Yeah, for example, there are modifications of balanced truncation that preserves positivity properties. So there are CDC publications on this, for example.
Thank you.
Last one? Okay, if not, let's take Anders again.